Hey guys, welcome back. This is part two of the kinematics with calculus part. Well, there's not a lot of calculus in this, but it's a good practice for us to look over like what the free response questions look like. So the first 100 meters of a 100-meter dash are covered in 2 seconds by a sprinter who starts from rest and accelerates with a constant acceleration. The remaining 90 meters are run with the same velocity the sprinter has after 2 seconds. Determine the sprinter's constant acceleration during the first 2 seconds. So you'd want to start by making a chart. Once you do that, you should be able to solve for both the acceleration and your final velocity. So I have 2 times the distance divided by the time squared is going to be my acceleration. So it's 2 times 10 meters times 2 seconds squared. And it looks like my acceleration is 20 divided by 4, or 5. My velocity will be this 5 meters per second squared times 2 seconds, and it gives me 10 meters per second. Determine the time it would take. So I want to go 90 meters. I already want 10. And I go 10 meters per second, so that's going to give me 9 seconds. So the total time would be 11 seconds, because this portion was 2 seconds. So for the first 2 seconds, I'm going to have a curved line. You guys will be able to do better than this. And at 11 seconds, I'm going to be at there, and this should be a straight line. I'm pressing the clicker, and I don't have it in the computer. Imagine that. All right, so we have an acceleration time graph, and they're asking us to make a velocity time graph. We start at a velocity of 0. So if my velocity is 0, my acceleration is 0, it is 0, 0. So for the first 5, it's going to be 0. From 5 to 10 seconds, my acceleration is going to be 4 meters per second from this graph. For 5 seconds, that's going to get me from 0 to 20. Right? So this is 0. This is going to be 4. This is going to be a straight line to 20. From 10 to 15, my acceleration is 0. So I'm going to stay at 20. And then from 15 to 20, I have a negative 4, so I'm going to go back down to 0. Determine the displacement of the elevator above its starting point, each of those 5-second intervals. 0 to 5 is going to be 0 meters. So I'm going to make 0 to there. From 5 to 10 is going to be this triangle. So it has 1/2. My base is 5 seconds. My height is 20 meters per second. So this is going to give me 50 meters. From 10 to 50, I'm going to go this rectangle, which would be 5 seconds times 20 meters per second, or 100 meters. So I'm going to go up to 150. Which is additional 100, and this is going to be additional 50, so this is going to be 200 as well. What's this graph going to look like? I need to be a curve to 50, because there's acceleration. As I draw a line, that's not a curve. I need to be a straight line from 50 to 150, and then I need to be a curve to 200. And this one should approach a slope of 0, and this one should approach a slope of 20. All right, so we have the ball that's being kicked, and we want to look at the components. My x component would be this side. So this is going to be 20 cosine of 37. Which is 16. My y component is going to be 20 sine of 37, which is 12. The fence is 32 meters away. So to get to the fence, it's going to be 2 seconds. So I'm only going to graph till 2 seconds, and this is going to be a horizontal line at 16. And I'm going to race back to 2 seconds because I was covering it up so I couldn't see it. The vertical component of velocity is going to start at 12. My slope needs to be negative 10. I know that I'm going to lose 10 meters per second every second. And so after 1.2 seconds, I'm going to be at 0. And then I can continue this straight line down to 2 because it's still the same slope. That should be a straight line throughout. All right, so you might have been surprised that this was 18% in the material, and that's because they throw circular motion in here. Although they have another part of your guys' test that's just gravitation too. So wherever you put circular motion, I make it a separate unit when I teach things, but very often it's thrown in with Newton's laws because it's another one of the F-nets, or you can put it in with orbits. So uniform circular motion, let's go over some of this stuff. Something is in uniform circular motion if it is moving at a constant speed. So only its direction is changing. So that would be special circular motion. Acceleration is a change in velocity. Velocity has both magnitude and direction. In circular motion, we're concerned with the change in direction. So even if the speed is staying constant, it is still accelerating. The special acceleration is a centripetal acceleration, and it is equal to v squared over r. So on your Physics C equation sheet, it shows up down here. You can see it's v squared over r. It's also written as omega squared times r, where this is the angular velocity. If you remember that our angular velocity is our linear velocity divided by the radius as long as there's no slipping. So we would get to that from there. In circular motion, your acceleration is centripetal. It is center-seeking. So is your centripetal force. Your velocity is tangential. So that means it's trying to go in a straight line. And it's inertia. The inertia, it wants to go in a straight line and wants to continue going in a straight line. So at any given point, your velocity is going to be trying to go straight. Very often we'll talk about G's. Here's Colonel John Stapp from the video I showed you guys earlier in the year. It's just a way to talk about the stresses that a body goes under. And very often those happen in moving in a circle. A G is just a factor of the 10 meters per second that we always feel. So if we're talking about our dragster at 15 meters per second, this would be, I'm feeling 1.5 Gs. I showed you guys the vomit comet. When they were raising us up, they were feeling 1.8 Gs. Over the top, they were feeling microgravity. We don't really say zero gravity for this. And then down here, they were feeling another 1.8 Gs, and they would do this over and over again. The portion from here to here, they're a projectile. And if you are moving as a projectile underneath the force of only gravity, you are weightless. I talked about the rotor, so the idea of the thing that swings you around. This is a common one in physics problems because the normal force is going towards the center in our picture, and there's a friction force holding the person up and balancing the weight when it goes down. So this shows up very often in multiple choice questions. I showed you guys the video with the centrifuge, the spinner they made for less than $1. All right, so in this circular motion, we were introduced to a couple of new things. And the first one was this idea of a period. And this is shown up again in simple harmonic motion, right? Because we have that sinusoidal activity where the graph comes back to the same place over and over again. This is the first time we did it. So this is a special time. In uniform circular motion, the period is equal to the circumference divided by the speed. So this is a special distance because it's one distance around. We also talked about period in terms of orbits, with elliptical orbits. We have this in our notes, so I'm not going to go over any of those. All right, this is good though. Okay, so we looked at this in the oscillations lab you guys did. You looked at a mass spring system. You looked at a pendulum system. And you looked at a dot on a circle. And a dot on a circle, the x and the y each made sinusoidal functions. What was the amplitude of your sinusoidal function? Your amplitude was 5. So the radius of the circle is 5 with this. And when your x is 0, your y is a max. And when your y is 0, your x is a max or a min. A max or a min. It's a or it's negative a as we went around. Right? If we're talking about our circle, if we're up here, our coordinate would be 0, comma a. If I'm over here, my coordinate would be a, comma 0. If I'm down here, my coordinate would be 0, comma negative a. If I'm over here, my coordinate would be negative a, comma 0. And so if you just plot the x or just plot the y, they're a phase shift off of 90 degrees, pi over 2 from each other. But this shows up very often. They'll also ask us sometimes to find out what the velocity is or the speed is. And the speed, you'd have to do the derivative of this, and then you'd be able to express what the maximum speed was for the x or the y, which would be 15. A racing car is moving around a circle track of 300 meters shown above. At the instant when the cart's velocity is directed due east, its acceleration is directed south. This works in that situation. So I know that I'm going clockwise. I can't be going at constant velocity because my direction's changing. My acceleration is 3. My radius is 300. So it looks like 30 would be our answer. A figure of a dancer in a music box moves counterclockwise. they want to know what the acceleration would be. You'd only have acceleration when you were turning direction, so from S to P and from Q to R, and you'd have none otherwise, and it's not going to build, right? It's going to be all or nothing. As soon as it starts changing direction, it has centripetal acceleration. As soon as it stops changing direction, it lacks centripetal acceleration. A car travels forward with a constant velocity. It goes over a small stone, which gets stuck in the groove of the tire. The initial acceleration of the stone as it leaves the surface of the road, our acceleration is centripetal. That means it needs to go towards the center. From the bottom of the tire, it would be going straight up.